I'm not Erdmann, I'm René. He gave me the advantage to talk today about the rare and frequently. Is it? No. Super. Rare and frequently overlooked N-glycan motif, this sulfation. I wanted to first give a short introduction. It's not going forward on this one. You did it. Okay, I move here. Andras and also his co-workers already introduced. I mean, SCE. They did their analysis with capillary electrophoresis. We are also doing our analysis with capillary gel electrophoresis. We call the whole thing glycodecoder, and this is actually an instrument how it could look like, but actually it could look like also like this or like this or like this. So practically we are hijacking all kinds of instruments which are on the market. The important stuff is actually only that what is inside. This is the capillary, like shown here or here. And what we are exactly doing is, or what we need is capillaries. The best is if they are in parallel, because then you can measure a lot of samples at the same time. We need a wavelength resolved detection for it, and this enables at the end of a spectral calibration that we can use an internal standard which is labeled with another fluorescence dye. And here, for our case, we developed over the last years a Glycome standard, so it's an oligosaccharide labeled with a dye which has another spectral properties, so it's emitting light at another wavelength. This means both are injected at the same time. They are separated in the capillary. They're excited by the same laser, which is important. And by a gating device, you can actually then record both electropherograms or two electropherograms in different spectral traces. Why we call it XCGLIF, multiplex. This means a lot of capillaries in parallel. So, and this is how a result looks. Before Andras and co-workers, they showed they are actually focused on the bracketing standard. This means they have the N-glycan pattern, like we have it here in red, and they would have also then in the red channel, they would here have before and afterwards some peaks. We went to a more universal approach where we have our ladder or our standard in another wavelength, which you see here in red. So we are recording them at the same time, and we then use these supporting points here, which are labeled with these Roman letters for the alignment. So we get at the end not the migration time in minutes, we get it in Glycome 4 units. This is how our standard is called. And you see here, this is peak number 6. Of course, there are coming also another peaks in front of it. To make it more universal. So N-glycans you detect in the late migrating region, and you can use the standard also for glycolipids, human milk oligosaccharides, monosaccharides, whatever you have, because if you have also here these other supporting points, you don't need to change it anything, you don't need to choose anymore. You only take the alignment standard and that's it. We also have a software, an automated software, Glückstuhl, which is also analyzing, which has a database inside, and it's then analyzing your electropherogram. Here you already probably recognize it's an IgG. And these are the glycans of an IgG. These are the neutral ones, and what is actually special for CE, this you also saw in the last talks. The charged glycans, they are not like an HBAC eluting at the end. They're having a negative charge, and this is why they are appearing a little bit earlier on the electropherogram. Or if you add another charge, they are appearing already earlier. This information will be important for later on. So, and yeah, for this one, it's exactly the same. So, higher charge early on the electropherogram. So applications, of course, a lot of people are going for biomarkers. You always have a droplet of blood. It's actually a rich source of biomarkers, and actually this was in the past actually done in the most of the cases and in the for the most samples with the HBAC system. And I only wanted to point out, we are of course not invented this alignment strategy with a ladder. Already Paul and Rudd and co-workers, and this is 96. It's almost 30 years ago. They also they invented already an HBAC method with a GU units, with the glucose units alignment. They had a database and they annotated it. So actually, they have done it already before, and This is still a not so nicely looking chromatogram, but they improved in the past, so now the resolution is also quite nice. I only wanted to point out a lot of development was already done in the past, and Gordon and others which measured the big cohorts, this was the basic work which was necessary, the annotation of these peaks to be able to measure all these big cohorts. So I have to say thanks. Pauline and co-workers, they actually started with it. So, and also we started not so a long time ago, but a long time ago, in 2010 already, we published the initial method actually where we used this multi-capillary electrophoresis instrument, and this is actually the electropherogram, how it looked in 2010. I was here for a visit in Manfred's lab, one of the most productive time in my life. Actually, we managed a lot within a short time, and this is an electropherogram, how it looked. But still, in this time, there were still a couple of open questions. Like if you look at the major glycan peak here, number 2 and number 4, they have exactly the same structure. Here's also no linkage typed on it. So, but during the next years, we came with an update in 2016. Where we were then able, by using a lot of different exoglycosidases, to find out that the major peak is this one with 2 to 6 linked salicylic acid, and this one here, number 4, has 1 to 6 and 1 to 3 linked salicylic acid, and also this ones we could refine. We knew, okay, 2 to 6 one, 1 to 3 one, and here it's not a core focus, it's an antenna focus. So this was actually a lot of work, and but it was nice. We knew then at the end more exactly. So at the end, if you look here at this ones, and if you separate them nice, you have something like 60 peaks, and you can annotate something like 90 different N-glycan structures. Of course, in HPC they have 140, but we are approaching it. So, but the important stuff here in the beginning, we actually displayed it in the initial publication. Later on in this publication, you're not saw this first part of the electropherogram anymore. There were also some peaks, and we did actually not exactly know what it is, so there are also no numbers on it. We knew this need to be N-glycans because APTS, which the label we are using, is specific for N-glycans, or specific for glycans, so it's not monosaccharide. The glucose is coming here quite early. It needed to be some N-glycan, and due to the fact where it's migrating, it needed to have a lot of charges. This is actually a result of an exoglycosidase. You see here the digest, you see here the electropherogram, and you see here the small peak. This is a later measurement, another person. This is why this peak is a little bit smaller. And you see here, don't wonder, this one with the asterisk, it's a marker peak. This is more or less a marker peak, which is saying to you, everything what is coming in front of it is no glycan, no N-glycan anymore. So as you see, if you want to have a faster migrating N-glycan, you need to add an additional charge. Here you have already a 4 antennary one with 4 salicylic acid. This means to come to this position, you need to add another salicylic acid so that you have more charges than antenna. And this is actually, in human it's not common, but in bovine, for example, the fetoine or the transferine, you see it, they have also an additional salicylic acid here on the glucnag. And the first thing what we thought, okay, then we have it also in human, most probably, but it isn't. If you look at this and you do a silase A digest, it would remove all 3 salicylic acids if it would be 3 salicylic acids, but you see by the shift it was only 2, and it ended up here. This is a quite small glycan. This means this glycan needed to be still charged, and it needed to have a charge of exactly 1. So phosphorylation was out. So we suggested it might be a sulfation of the glycan. But actually, how can you prove that it's sulfation? You can take an exoglycosidase digest, or you can do mass spectrometry analysis. But it's a bit shifted here with this. But unfortunately, there is no exoglycosidase available. At least it was not in this time, where you can only say, I'm adding it and it's cleaving my sulfation and that's it. And unfortunately, APTS is not, it's incompatible with more or less incompatible with MS, so you can actually not detect it. So we had a problem. We knew it somehow that it was a sulfation, but we could not prove it. If we would publish something, so everybody would say, nice try, but the lucky thing, New England Biolabs came to us and said, if you would like to have a exoglycosidase, which one would it be? And we said, sulfatase, of course, because we want to find out if it's really. So they said, we can try it. So later on I will come back to this topic, but they were successful, quite successful. And we went to solve the issue with the MS analysis over a removable dye. By the way, we published, because it was a groundbreaking work in our eyes, so we published it in Engineering, a nice and quite high-ranked journal. And as I heard, they have each year another issue which is only dealing with glycans. So if you have a groundbreaking work and you want to have it published, and that a lot of the community sees it, publish it in Engineering. So removable dye, a great thing actually. What is it? You have the N-glycans attached to the protein. We are releasing them with PNGSF, and we directly label them at FMOC. It's actually in protein science, it's a well-known compound for the protection of groups. So and exactly this one we use to label our glycans. And the great thing is, you can detect it then, you can separate it in HPLC, and you also can detect it with your fluorescence detector. And so we were able to fractionate actually our glycans. And with these fractions, you could directly go to multi-TOF MS analysis, because of FMOC also makes it more sensitive, great. Or you remove the FMOC. Here, it's swimming around, and then you're free to label your glycan with whatever you want, 2AB, APTS, procainamate, whatever you want, and then you can actually combine it with all kinds of other methods. And this was actually great. So we chose as a model protein, we chose the human IgA. Where here, this glycan peak is also inside, but we chose the IgA because this glycan peak inside was huge, not like in plasma, a tiny little small one. That's a quite big one here. And it's nicely separated from all the other N-glycans. So, and this was actually this is at the end the structure which comes out. Our first idea was probably the sulfate is added here somewhere on the galactose, but actually it was not. So fraction number 16, you can see here, it's a nice single peak which was separated from this one here. And if you add the sialidase on top of it, you see that the peak is shifting to a position where it's not charged. If you add an beta 4 galactose on top of it, you're only able to cleave one of the galactoses, so which is only a small move. And for a glucna case, what you add, you also only have a small move, and it's moving to smaller. But still, it's getting smaller. If you would lose a charge, it would go to later migration times. So this means we were not able to remove the sulfate. And this time, so we found another galactosidase which was able to cleave at the end both. So it cleaved both, and what you see is getting smaller. It's migrating to earlier, or it's going to earlier migration times. This means the sulfation is not attached to the galactose like we expected in the beginning. But if you remove both glucnacs, you can see it's shifted there. It's getting bigger, or it's getting to later migration times. So the sulfate is actually, by the database, then we could say, okay, it's on this arm located. And of course, we also went to Mali, otherwise nobody would believe us. The FMOG label, we could get a Mali spectra. It was not easy, you need a lot of sample. And we also got an MS spectra, so everything was publishable, and we published it, and it was great. And in the meanwhile, New England Biolabs was successful with finding sulfatases, and they found a couple of one which are actually active on sulfate. And they came back, or Lea came to us in Magdeburg, and she was testing it then on N-glycans. Not all of them were successfully on N-glycans, but we find one which was really nicely working. And you see here, this is the initial glycan, but unfortunately it could not, if you add the sulfatase, it could not cleave this. You needed to remove salic acids and the galactoses, and then you could remove also the sulfate. And this is only working in a surrounding of a co-ion of calcium chloride. Nothing else was working, so this will also be important for later on. So nice. And while Lea was doing her work and was producing the enzyme, there was also another publication of us coming out from Franja, where they also looked at the glycopeptides. And they could at the end, Franja and Marcus, they could at the end annotate, and they could show where exactly is the sulfate attached to which site. So a small recap, already in 2010 we saw these peaks. We could we could not prove it exactly, but we could we thought that this is sulfated by exoglycosidase digest, which shows human IgA as a model protein. in 2021 there was the sulfatase published, the FMOG labeling was published 2 years later, and also the identification of the sulfated peptides on IgA was published by Franja in 2025. And if you want to know where else could it be in plasma, I can only refer, Franja also published a second publication where she looked at the low abundant glycoproteome of the human blood, and there's a table S10, there are a bunch of other glycoproteins inside where it's also attached. Nice work, by the way. But what about IgG? This is probably what is what you're interested in. Of course, IgG has it also. It's exactly the same glycan, exactly on the same position like for the IgA. IgG has it also, and we were actually happy to see a Nature Communication publication where they said, we found sulfated N-glycans in traces for rheumatoid arthritis patients, and they said it's a biomarker, and they saw it, and we said, great, they also see it, fine. So we are happy. But actually, shortly after, there came a reply on this publication where they practically said, you should be carefully control your IgG, which you purified from plasma, because of the glycan H5 and 4-S2. This is actually this one without salicylic acid and without the fructose, is quite high in your sample. So it might be, if this glycan is high, this is the major glycan in plasma, it might be that your purified IgG has impurities, a lot of other protein impurities from plasma inside, which might also bury this sulfate. So you can actually not say it. And they replied also on this one and said, our IgG has a purity of 95 IgG1 of 95 and the other one of 99%. So we believe that it's really coming from the IgG. So we also looked you can also look in Franja's table, and you will find no glycopeptides. So now's the big question, who's right? Is it on IgG or is it not on IgG? And actually, I have to say, we are analyzing the released glycans. We have exactly the same problems like then. We don't know on which protein is it attached. We only see it in the IgG fraction. So, and to answer this question, we came this year out with a publication, Radar of the Lost N-glycans. It's not only sulfation, there's also bicyclic LACNAC elongation we also saw. But anyway, so we started exactly like other people start. We took the blood. We captured the IgG in blood, you see it here in the beginning, and also an IgG even smaller here, 0.01%, 0.02%, depending a little bit on the patient. It's a really, really tiny peak, but it's there. And we went ahead and we said, why these other people don't see it? So we wanted to localize it. So we did an IDIS digest, on-beat IDIS digest, where we have the FAB fraction and the FC fraction, and we looked inside, and for the FC fraction you practically see nothing, but for the FAB fraction you see a huge peak. This means it's most probably attached to FAB. We also did LC-MS based proteomics to find out how much impurities are inside, or if we also see impurities, and yes, of course, we had a few of low abundant proteins. The major impurity was the albumin, which is not glycosylated, and complement factor C3 and also C4 a little bit. C3 has mainly oligomannose and glycans attached, so it might be also not, it was never described as a source for this. So anyway, but to be really sure, we added our sample to SDS-GL. You can see here in lane number 1, this is the initial blood with the albumin quite big. This is a standard IgG from Athens, which we bought. Here you see our purified, our captured IgG, the FAB fraction with the IDIS inside, and the FC fraction here. And we did also here a LC-MS-based proteomics approach, and we could then, to each of these bands which we excised, we could then also say exactly which kind of IgG part is inside, because we only looked which glycopeptide we can detect inside of the LC-MS, and then we said, okay, we could only detect glycopeptides inside from this part of the IgG, so this means it needed to be this. Fine, and we did a CG-LIF analysis. And we found, of course, here again the small peak from the GL, a big peak with more than 1%, and for the FC fraction, exactly nothing. So this means, for the LC-MS analysis, we could detect only traces of impurities. And if you think about that, if you have traces of impurities inside and they have only the sulfated glycans, and you would sum them all up, you would not end up then more than 1%. So it's highly possible that it's really only on the FAB glycan. So, okay, I don't know how much time I have, but of course we use also the sulfatase to confirm that it's really a sulfated glycan attached. So we took the Fab fraction, we removed salicylic acid and galactoses, we added it actually on the sulfatase, we added the whole mixture, we washed away all the not sulfated glycans. The sulfated glycan was sticking to the enzyme, and then here we not used the cofactor, this calcium chloride, to elute it, to cut it. No, we destroyed the enzyme to release the sulfated part, the sulfated N-glycan. So, and you could see here it's mainly the sulfated N-glycan, so it's fine. It was really a sulfated N-glycan. So yeah, we could confirm it, but at the end the big question is why you cannot see it on glycopeptides. And most of you might already recognize it if it's on FAB part only. You have the variable domains in this region, exactly the hypervariable domains. So you have a lot of different amino acid sequences which are here possible really to bind the pathogens and so on. So, and if these glycans are attached here in this variable domain, it's almost impossible to detect it with MS, because of you have a big variance of different glycopeptides which are there. And often also for MS they only looked at the conserved glycosylation site. This is why it was also not reported before, why was it never seen in helic UPLC or HPLC analysis? Also, if it's there, our last publication, Burok et al., gives an electropherogram of IgG where it's annotated, and also a possible reason why it was not annotated or detected before. So thanks for your attention. Also thanks to all of our cooperation, or to all of our colleagues, to all of my colleagues which did the work. Of course, it was not done at Glycera only. A part was done at Leiden, in Leiden, a part was done at the Max Planck Institute, and a part was also done from New England Biolabs. Thanks again. Here are the publications if you're interested in it, and now I'm happy to answer your questions.
Thank you.